So the first one is in preliminaries, looking at some set theory and the idea of, well, what I was drawing your attention to there in the reading notes was to the issue of equivalence relations, and also the terminology about functions, well-definedness, one-to-one, onto, etc. Okay. So the first, so in the set of exercises there at the end, I mean, there's tons of exercises here, many of the same type, especially these early ones on set theory, many of them of the same type. But one in particular I picked out there was question 11. And so this is quick, and this is probably revisiting some first year material, but we'll have a look at it to remind us of a few things. So question 11 here is what to focus on. Yep. So question 11, prove, okay, we're going to revisit the concept of Cartesian product here as well. So on the left-hand side, you've got the Cartesian product of two sets. So A, B, and C are sets. You've got the Cartesian product of two sets, one of which, the one on the right is C, the one on the left is A union B. And on the right-hand side, you've got the union of two sets, both of which are Cartesian products. First one A cross C, and the second one B cross C. Now, when we talk about a proof of this, really, the proof is really just going to be showing how this statement about sets kind of translates into an equivalent statements about logic and so on, and using the kind of standard things about logic and the way and not and interact, etc., we'll be able to prove. But we also are illustrating here a general principle and a general approach that when you're asked to show that two certain sets are equal, a common approach to do it is to do it in two ways, to do it in two parts. Firstly, to show that the set on the left is a subset of the set on the right. So you know the left-hand side is included in the right-hand side. And then, secondly, show that the right-hand side must be a subset of the left-hand side. To show that the two sets are contained in one another, and how can two things be contained in each other? Only if they are in fact the same set. Okay? So that's it isn't necessarily that you have to do it that way. Often you can demonstrate the equality in just one movement of a chain of logical equivalences, but let's do it the two-directional way because it illustrates the point well. Okay? So we'll demonstrate here. We'll demonstrate that each is a subset of the other. It's clear what we're talking about. Each is the two sets on either side. It's good to put these little introductions in because you know what you're doing. One, and the reader knows what you're doing. So we consider an element x which is in the set on the left-hand side. Okay. So we select a general element x which is on the left-hand side. We're going to examine x, and hopefully by examining the properties of x, we should be able to see that it must be in the set on the right-hand side. So we'll get a chain of implications. Now, what does it mean for x to be in this set? Well, see, this set has a complicated structure, but you want to start from the top level and work down. The top level structure of this set is a Cartesian product. Okay? So for x to be in that set, it must mean that x is equal to some element x1. So it must be a pair, an ordered pair of elements, an x1 and x2, where x1 is some element of A union B, and x2 is an element of C. Okay. Okay, that's good. We're now seeing x as an ordered pair of elements. And we're going to be trying to show that x is an element of this set on the right-hand side, which is a union of two Cartesian products. So the element at least does have the correct form. It's an ordered pair, so it does have a chance of being in one of those Cartesian products. And then really what we're doing is the only kind of operator still in play here is this union operator. X is an element of x1 is in A union B. The meaning of that is x1 is in A or x1 is in B. One of those two conditions holds. So we can say that it's either the case that x1, so x is equal to x1, x2, where x1 is in A, x2 is in C, or, so this union set operator in effect becomes this logical OR operator, or it's the case that x is x1, x2, where this time the x1 is in B and the x2 is C. You can see why I've laid it out like that, because now I've got x is equal to this or x is equal to that. And that OR, remember, OR and unions are very much equivalent things. So this statement here is saying that x is in Cartesian product of A, C. Because x is an ordered pair. First element comes from A, the second element comes from C. Well, that's exactly the definition of the kinds of things that are in the Cartesian product A cross C. We still got this logical connective here. And what's this bit saying here? This is saying x is in the Cartesian product B cross C. So x is in this set, or it's in that set. That means it's in the union of the two. So yeah, that's the definition. So that implies x is in the union of A cross C. Union of B cross C. It's perfectly possible that x is in both sets. If A and B have a non-empty intersection, our x1 here could be living simultaneously in A and B, but the point in this argument is that it must be in one or the other. It could still be both. Okay, so that implies, this shows that the set of the left, A union B, Cartesian product with C, is contained in the set on the right. And that's half of the work of showing that the two sets are equal. Okay. We would then go back here and have a second argument now to show that the set on the right-hand side must be a subset of the set on the left-hand side. Any questions about that argument or comments about it? Would you be very impressed if I spent the next 3 minutes doing out a similar length argument to show the inclusion the other way?
Is it not just in reverse?
Exactly. Yeah. So I remember I said at the start, we're going to show inclusion both ways. I said sometimes you can quite efficiently show the equality directly by just showing that being in the set on the left-hand side via a chain of equivalences becomes exactly logically equivalent to being on the right-hand side. Well, then that means the two sets are equal. And you're very right. You shouldn't be very impressed if I start laboriously writing things out again, because really, all I have to do is just appreciate. Now, that's good intuition, but we should check it. Check that each of these implications, in fact, also works the other way around. Okay, so let's just check that. So now I'm starting at the bottom. So I consider an x in the union of these two sets. Okay, does that imply that x is in the first set or x is in the second set? Yeah. What do you need to justify that? Well, that's just the definition of the union operator of sets. Something is in the union if it's in one or it's in the other one. Okay, so that's good. I can stick this, do it in a different color so we'll notice it was added later. Stick the green arrow here. So if I'm here, if x is in this set or x is in that set, well, this statement here is really just saying the same thing. I've still got this or in the middle, but I'm just writing out the definition of this Cartesian product. So x is an A cross C. That does mean x is this form here, where the first bit comes from A, second bit from C. And x being a B cross C, that just translates into that. So that implication goes the other way from here back up to here. And from here, can we get to here? Yeah, because the work done between these two steps is just the passing from this union operator here to this OR statement here. The x1 is coming from the union, so it's either the case that the x1 is coming from B, or it's the case that the x1 is coming from A. So these two we see now are exactly equivalent. And well, this really is, it wasn't just an implication, it really was an equivalence. Being in this set is equivalent to having this structure. It's just the definition of being in this set in the Cartesian product. So yeah, in fact, we did it quite well. We did work efficiently there. So it really was a chain of equivalences. In fact, we notice our original argument was in fact a chain of equivalences. So these green backward arrows added afterwards. So the inclusion works the other way. Set inclusion, this statement, this set inclusion can be reversed. And the sets are equal. The sets I'm talking about are the two sets in the question at the start. Okay, they're in fact the same set. Okay, that's good. That's a quick, what we're seeing there is just getting used to dealing with sets again, Cartesian products and so on. And also this point, in general throughout this course and in general throughout mathematics, when you're building arguments, this implies that and this implies that, it's a common thing to do. It is always worth checking, is this really just a one-way implication, or am I in fact passing through equivalences? Because then you might actually be doing more than you think, which is good. You might actually be demonstrating more of it. Okay. Any other questions about that? We'll move on. We are going to meet Cartesian products a lot, okay? Because taking a set and forming the set of ordered pairs, it's quite a common construction. It's quite a common way of building more complicated things out simply. Okay, the next one on the list. Well, I've got 17, 19, 25, and 28. Just keep an eye on time, so I wanted to do some from chapter 2 as well. 17, yeah, so some of these we'll maybe just discuss between ourselves. 17, 19, 25, and 28. 17, 19, 25, 28. 28 is a nice one, I want to talk about that. 25, certain relations specified. We have to decide whether or not they're equivalence relations. It's kind of a discussion thing. Okay, so 17. So 17 are candidates for functions from the rational numbers to the rational numbers. The rational numbers, by definition, it's a set of all fractions of integers. However, and this is an idea. I mean, the reason this exercise is here is not so much for the importance of the thing itself, but this theme where you've got a set, but really there's an important equivalence relation on the elements of the sets. You see, because rational numbers, okay, we say they're fractions of integers, but there are lots of different fractions that are in fact the same as one another, or should be regarded as equivalent. So 1/2. Okay, it's a different fraction than 2/4, but really it's representing the same numerical quantity. Okay, whereas when you sit down and you try and give a definition for a function on the rational numbers, we're defining it here in terms of the fraction. So there's a basic question here is for all these what look like, on the face of it, good definitions of functions, we have to worry about, are they well defined? They're supposed to be functions from the rational numbers to the rational numbers. So if I evaluate f and a half, 1 over 2, using this rule, so p is 1 and q is 2, will I get the same answer as when I evaluate it on f of 2 quarters? Because 2 quarters is the same rational number as a half. If I don't, then the thing doesn't qualify as a well-defined mapping, because well-defined for a function means that if you give it an argument, a particular rational number, it must give you a uniquely defined value on that. There mustn't be any ambiguity. So probably we're going to look at these, throw a few quick examples at them, see if they're behaving in a well-defined way. If they are, perhaps it is well-defined and we might be able to prove it. If not, we'll hopefully quickly find a counterexample. So what about the first one? Yes or no for well-defined? No. So have you got an example that will show that?
The half and 2 quarters.
Half and 2 quarters, yeah. So f of a half by this rule would be 2 over, well, straight away we've got a problem. 2 over 0. Is 2 over 0 a rational number? No, it doesn't even qualify. So it's not even the fact that it's not even well defined. It isn't even defined at all on all of the possible things you can stick into it. So that falls down straight away. But as well, if you tried to put in f of 2 over 4, you wouldn't get 2 over 0.
That's not correct either, because p on the denominator as well.
Oh,
q.
Oh, sorry. That's not q. Sorry. I was misreading it. So p. So it's a -1 there. So that's giving us -2. So sorry, if you do f of 2 over 4. And so that's going to be 3. Okay, here's where we run the button. Yeah, 3 over 0. So that's shriek in horror at that point. Can't have 3 over 0. So certainly not well defined. No good as a function. It would be okay as a mapping from the abstract symbols of any integer over any other integer. It does perform perfectly well, and so then you would be allowing a 3 over 0 if you're just considering this abstract system of, fractions. But it ain't no good as a function from the rationals to the rationals. What about b? Yes or no for b? Yeah. It looks good. It looks good as a legitimate mapping. Yeah. So yeah, what are we doing? So when you evaluate it at f of a half, 1 over 2, you get 3 over 6. Again, that's a half. I mean, algebraically, we notice, of course, we're multiplying it by 3 and multiplying it by thirds. We're only multiplying it by 1. So in effect, we recognize, so f of p over q, it's 3p over 3q. That can be cancelled down to p over q. So in fact, this f from q to q is simply the identity. The identity function. The identity function that sends every object to itself is a perfectly good mapping. It's a mapping that exists for every set. Except maybe the empty set, but yeah. It's your kind of first example of a mapping of any set. The identity. And what about what about C? Good or bad on C? It won't work. Have you got a counterexample?
Using the half and the
Using half and 2 over 4. Yeah. So in C, f of 1 over 2 is 3 over 4, whereas f of 2 over 4, I'll just go right to left here, f of 2 over 4 is 6 over 16, all right? 6 over 16, and whatever they are certainly not equal.
So f of a half does not turn out to be the same as f over 2/4, and that's no good for a function that's supposed to be from the rational numbers, from the domain of the rational numbers, because a half and 2 over 4 are the same rational number.
So this is not well defined. And remember, all we have to do as a function q to q, all we have to do is just find one example, one counterexample where it falls down. Because to be a well-defined function, you have to be well-behaved everywhere in the domain. Okay, one place where you fall down is enough to describe. But of course, there's nothing special about a half, 1 over 2, and 2 over 4. If you throw any pair of similar fractions at it, it's going to show the same behavior. D, our last one there. Well, by the law of averages, we've had 2 failures and 1 success, so maybe this, let's suspect a success. Does it look like a success? It looks okay. It looks okay, because you're taking some rational number, okay, represented as a fraction, here, q. You just start to see how it's built up. So just ignore everything except the square. It's p squared over q squared. Well, that's just taking the number and squaring it. That's how you square a fraction. You square the top, you square the bottom. That's the same as just squaring the numerical quantity. And then you're multiplying it by 3/7. That will behave the same no matter how you represent the fraction. And then you're subtracting p over q. You're subtracting the original number. Yeah. So D looks okay. And in fact, we can give, in fact, it is equivalent to, if x is a natural number, a rational number, this f of x, we can just define it in a fraction agnostic way. So we can give a formula for f that doesn't depend on the particular fraction you choose to represent the rational number. We can just say f of this rational number x, 3/7 of x squared minus x. That's really what the function is, isn't it? So it's just a polynomial function. Polynomial functions are perfectly well defined on the rational numbers. They just operate on the, on the numerical quantity. But the more general point where, the reason, and there will be points later on in the course where we refer back to this idea. Okay, we think of the rational numbers as being the fractions, but really they're not. Really they're equivalence classes of fractions. So the rational number a half is actually a whole infinite bunch of fractions. 2 of the fractions in there are 1 over 2 and 2 over 4. But really there's a whole bunch of things here. And it's the same for every other rational number. They're really an equivalence class of fractions of integers. So if you sit down and claim to be defining a function of the rational numbers, and the rule that you're giving for it is given in terms of the fractions, to be well defined, you have to be sure that the value the function claims to give is the same for any of the equivalent representations of the same rational number. If we want our function to be a function on the rational numbers, okay? And so that type of situation is going to occur later on, because we're going to be looking at our groups, and one of the operations we're going to do on groups is we're going to change them and reduce them and project them, and we're going to form this operation of splitting up a large group into equivalence classes to form a kind of simpler, smaller
group associated to it, and we're going to define functions on this new group. But they're going to have to be defined, the actual computational rules for the functions will have to be defined in terms of the individual elements of the original structure. And this is one issue we're going to have to worry about. We're going to have to worry about well-defined ones. But this is an illustration of that matter in perhaps a simpler setting of rational numbers and functions. Any related questions at the moment? Okay. So I might skip a question or two because there's one at the end here I'd like to get to, and then I'd like to look at some of the ones in the integers chapter. But just to appreciate that there is plenty of work here. I don't think you're ever going to have an excuse of, oh, I don't know what to do for my work on number 3. There's a whole lot of ammunition here on the group theory. Okay. So these questions 25 and 28, these are focusing on equivalence relations. So what are equivalence relations? They're going to be an important tool we're going to use from time to time in studying group theory. So a relation on a set is just some kind of logical relationship that's you set up between the elements, and it's a logical statement. So either a pair of elements are related to one another or they're not. Examples are things like the ordering relation on the integers, or one numerical quantity being greater than another, for instance. So for any particular pair of numbers, either the left one is greater than the right one or not. So it's a relation, a clear logical statement for a pair of elements that's either true or not. An important class of relations are the equivalence relations. And these are the ones which most closely mirror the very important relation of equality. So strict equality is kind of a really very fundamental relation. Is this thing the same as that? Well, there's a whole other bunch of relations which act like equality in important ways, and these are called equivalence relations. And these ones, there's 3 properties. Can you name them? 3 properties? The 3 properties of an equivalence relation. So let's do a quick review before we get to considering these things. Yeah, the 3 important aspects of an equivalence relation are reflexivity, symmetry, and transitivity. Now the relation here, here the relationship is represented as membership of the ordered pair in a set R, but I'm going to write out the other versions because he passes quickly from talking about relations in terms of set membership to talking about them in terms of twiddle. So twiddle is a equivalence relation on a set X if, well, the first one is reflexivity. So every element is equivalent to itself. Every element is related to itself. That's reflexivity. Symmetry says for every pair of elements, if the relation goes one way, it must also go the other way. Okay, symmetry is a good name for that. If the thing exists in one direction, it must also exist in the other direction. If the relation satisfies that, it's called a symmetric relation. Okay? Now, a clear example of one that doesn't satisfy that is the numerical relation of greater than. Okay? 4 is greater than 2, so 4 is related to 2 in that sense, but 2 is not greater than 4. So greater than on numerical quantities is not a symmetric relation. And the last one is transitive. And this refers to when you've got 3 elements in play. If x is related to y and y is related to z, this must imply, these 2 facts imply that x is related to z. And this is transitive.
Transitive, I also like to think about it as saying that the relationship travels through intermediates. The relationship travels through intermediates. So the intermediate element here is y. So x has a relationship to y has a relationship to z. If it's always the case that that would imply that the first element, the relationship travels through y, and x is in fact related to z. If that's always the case for every triple of elements, then that relation is called the transitive. And if you got all three, it's called an equivalence relation. Okay? And this is going to be an important operation for us on groups later on. It's a way of taking a large set, and just as I did with the set of rational numbers there, look, what I started with was the set of fractions, fraction symbols, which is a big set, and we carved it up into segments. All of the ones that represent the rational number a half, all of the ones that represent the rational number a third. The way that is done is by setting up an equivalence relation here. The actual what is the equivalence relation on the fractions? So A over B is equivalent to C over D. What's the meaning of that? And this is kind of a subtle question. So what we want to say is like a half is equivalent to 2 over 4. We want to say that two fractions are equivalent if they're representing the same numerical quantity. But we want to do it in such a way, you see, this is done as a way of constructing the rational numbers from the integers. So can we get a definition here for this relationship, but only using concepts from the integers? Because this is done as part of the operation of constructing the rational numbers, it's building them up out of features of the integers. So there's a simple statement we can put here, which tells you exactly when two different fractions should be regarded as being equivalent, as representing the same rational number. So to discover it, you want to kind of imagine this equivalence being an equal sign. And can you state the equivalent statement in terms just of pure integer information? The A, the B, the C, and the D are integers. So if I did have an equal sign there, and you see, I don't want to refer to the operation of division, because division is something which isn't defined on the integers. It takes you out of the integers. So if this was an equal sign, is there some neat way of expressing the equality without referring to division? Sorry?
Could you put like NA over NB, like some kind of factor of form?
Yeah, something. It's going to be something equals something. But how could you get rid of the operation of division? Cross multiply. Yeah. So the statement would be that A times D has to be equal to C times B. So try it out with the half and the 1 over 2 and the 2 over 4. You were saying is 1 times 4, which is 4. Does that equal 2 times 2? Well, yeah, it does. 2 times 2 is 4. So this comes from thinking of the equal sign here and cross multiplying, so that you're able to state the condition for the relation purely in terms of integer information. So this is an object statement which makes perfect sense in the. Okay, I'm abusing notation here, saying this is an element of the Z, but this statement makes perfect sense in the Z world. We don't need any other information to talk about this statement. But it lies at the heart of constructing the rational numbers. Because it's the correct statement that gathers together all the fractions that represent the same numerical quantity. And it partitions the space of fractions into this partition space, which turns out to be the rational numbers. Okay. So that was a divergence on the way to question 28. Scanning these pages will go in later on, of course. 28, okay. Yeah. kind of a trick. Well, no, it's not a trick question, but it's a subtle point. So equivalence relations have these three properties, and these are the three parts of being an equivalence relation. However, this question 28 is giving a bit of a challenge to you. It's saying, well, there's an error somewhere in this following argument. Now, this argument is in quotes to alert you to the fact there's something wrong with it. But this person who's saying this is claiming that actually, what they're claiming, the reflexive property is redundant. We don't need to have this separate axiom of reflexivity for an equivalence relation. This person is claiming that reflexivity is implied by the combination of these two. And here's their argument, and it seems pretty convincing. If x is equivalent to y, by symmetry, y would be equivalent to x. But then if we also have transitivity, you see x is equivalent to y is equivalent to x. By transitivity, the relationship will travel through y and tell us that x is equivalent to x. That argument seems pretty convincing. It is quite convincing, but it's not 100% convincing. There's a fatal flaw in their argument there. Okay. It isn't the case that reflexivity is redundant, but it would appear to be from this argument. What are they slipping past you? There's a sleight of hand performed there in that argument. So it's taking a value x, and it ends up by showing that x is equivalent to x. Hey, well, that's a good one to puzzle through today. Have it running through your mind, and we'll discuss it again at the lab session. Okay. I'm itching to tell you the answer, but that would disturb that. That would. So mull that over in your head. So it's claiming to show that reflexivity is not necessary. Okay. Something to think about in your lunch break. Any other questions remaining from chapter 1 or from that preliminary material? Now, don't be put off. There is a whole raft of exercises. I mean, I doubt you're going to get through them all, but there's plenty of ammunition there for practicing them. But there's few key things of sets, equivalence relations, mappings that we want to be comfortable with talking about in our latest. Okay, we only got about 10 minutes, but chapter 2, this is, we covered all this material in detail in our study of number theory last year. And this is really just a quick trip through some basic number theory that we're going to call upon in our study of. Basically sets up the principle of mathematical induction, which is an important proof technique. It looks at the basic ideas of divisibility, prime numbers, the integer division and greatest common divisors, and the way every integer factors into a product of products. Now, relevant questions I picked out here. Well, one was example 2.4, and then questions 4, 6, and 7. What was example 2.4? Yeah, example 2.4 I put there as a nice. It's a good, honest to goodness, strong, decent example of proof by induction. And it's quite a fundamental, important idea. So this is the Binomial Theorem, which expresses how you raise a sum of two quantities to any integer power, and it gives it to you as a big, long polynomial in A and B, and it's describing exactly what the coefficients of the polynomial are. And it's dealing with this permutation symbol. Permutation symbol or the choice symbol?
permutations, these binomial coefficients. Okay.
So I think it's very good for you to have a read through that, and it's a good, some of the early examples of proof by induction can sometimes feel a bit babyish or a bit like toy examples. That's a nice, decent, fundamental, important application of induction. Well, let's take a couple of the exercises. So 4, 6, and 7. Have a look at these. Oh, we might only get one done. Let's have a look at question 6. I think question 6 is a nice
demonstration of proof by induction.
So we're reviewing here some basic facts about divisibility, and also having a run through with proof by induction. And proof by induction will occur in a few places in our study of groups. So what we're trying to prove here is, so this is section 2.3, question 6. For every natural number n, we want to show that 99 divides this large quantity. 4 times 10 to the power 2n plus 9 times 10 to the power 2n plus 1, and plus 5.
Okay, this screams out to use induction. It's an infinite set of statements indexed by the positive integers for the natural numbers. So clear candidate for induction.
So first of all, we check the base case. Where n is 1. Well then, 4 times 10 to the 2n plus 9 times 10 to the 2n minus 1 plus 5. What is this actually equal to? It's 400 plus 9 times 10 to the 2 plus 90 plus 5, so it's 495. And yeah, 495 is 5 times 90.
So the base case checks out. Base case is true. These proofs by induction, they all follow the same pattern.
Establish the base case, make the inductive hypothesis. So now we assume that 99 divides this 4 times 10 to the 2k plus 9 times 10 to the 2k minus 1 plus 5 divides all that quantity for some k greater than or equal to 1. And it's a valid assumption to make because we know it works for at least one example of k. So it works for k equals 1. So we are on secure ground to make this assumption that it holds for some k equals 1. And now we try and deduce the equivalent thing for k plus 1. Now, of course, when we say that 99 divides that, specifically what we're saying is that this large quantity is equal to 99 times q for some, oops, q's look a bit too much like 9s, it's a bit confusing, but for some natural number q, this large quantity in the brackets is 99 times q. That's what the divisibility is. For some q. There exists a q such that the bracket is equal to 99 times q. Okay, so we attempt to go one step further. We look at 4 times 10 to the 2k plus 2 plus 9 times 10 to the 2k plus 1 plus 5. Okay, so that's the quantity where n has been replaced by k plus 1. So we have 2k plus 2 and 2 times k plus 1 minus 1, which comes out as 2k plus 1. Now this quantity, And the recognition here, and it's similar kind of thinking in most induction proofs, this quantity looks very, very similar to that one. It's almost the same. So we just want to tease out the relationship. And the way to do that is to make this quantity appear in our expression. Now it's almost there, but the indices are different. So we want to work on this a little bit and draw this quantity out. So how can I make, so the thing is operating on the indices. So I want to make this index be 2k. So that means I need to split off this factor of 100. So I can put 100 out here. So 100 times 4 times 10 to the 2k. And here again, there's a factor of 100 in the difference, isn't there? Yeah. Plus 100 times 9 times 10 to the 2k minus 1. And then the 5 is still sitting there.
Now that's good because we've made the correct indices appear. 10 to the 2k, 10 to the 2k minus 1. And we've still got the 4 there and the 9 there, which is good. We've still got the 5 sitting there. But these factors they're complicating things, these extra factors of 100. So if I really want to make this expression appear, I want to separate off. So you see, I've got 100 of these, but I want to have only one of them. Similarly, I've got 100 of these 9 by 10s to some power. But really, I only want one of them, 9 by 10 to some power. So the extra baggage that's hanging around there can be expressed as, well, I've got 99 times 4 times 10 to the 2k, and a 99 times 9 times 10 to the 2k minus 1. So haul that baggage to the front. Then what's left behind is plus 4 by 10 to the 2k, plus a 9 times 10 to the 2k minus 1, and then my 5. And I'll bracket that quantity there. Okay, you see what we've done? We've now successfully brought out exactly the relationship between the expression when we've got k plus 1. We've exactly see how that relates to the similar expression when you've got n equals k. So we've got the similar expression there, and we've all this extra baggage. What's the good thing about the extra baggage that we see? It's divisible by 99. It's clearly a multiple of 99. We've got these two 99s sitting. And we already know by assumption, by the induction assumption, that this bracket is a multiple of 99. So we're just adding together a load of multiples of 99. And by property of divisibility, if you're adding together a load of multiples of 99, the whole thing is a multiple of 99. In fact, we can explicitly write this out now. It's 99 times 4 by 10 to the 2k plus 9 by 10 to the 2k minus 1. And then this is our 99 times q. Oh, sorry, I should have just added in a plus q. 4 by 10 to the 2k plus 9 by 10 to the 2k minus 1 plus q. So this q is the same q from up here. So we've shown clearly that this quantity is divisible by 99. So this is the required result for n equals k. So we've established the base case. We've made the assumption for n equals k. From that, we deduce that the thing is true for n equals k plus 1. So by the principle of induction, the whole thing is true for all natural numbers n.